Hi everybody, welcome to another video in my series on computer systems. This video will be the start of Module 3. We're still talking about material from the book Computer Systems, A Programmer's Perspective. This is covering the material in Chapter 6, and we'll focus on cache memory in Module 3. But for this video, let's talk a little bit more generally and start by going over something called the memory hierarchy. But before we get to what the memory hierarchy is in and of itself, let's talk about some types of memory that we're probably familiar with and just some terms that we need to know and how some of these things work. So the first thing is random access memory. Now the key features are that RAM is traditionally packaged as a chip. The basic storage unit is normally going to be called a cell, and we can hold 1 bit per cell. So when we talk about the cell of RAM, we're talking about enough storage to hold 1 bit. And we have multiple RAM chips that form a memory. So this is when we say, oh, I'm going to buy a laptop and it's got 4 gigabytes of memory. Well, what we're talking about there is RAM. We're talking about random access memory. And that comes in 2 different varieties. We've got SRAM or static RAM and DRAM or dynamic RAM. So let's take a look at the difference between static RAM and dynamic RAM. Well, we have a table here that kind of just shows us the major differences that we want to be aware of. Whereas static RAM takes 4 or 6 transistors per bit, dynamic RAM only takes 1. However, when we take a look at access time, we find out that dynamic RAM takes 10 times the amount of time to access as static RAM does, which makes it 10 times slower. Static RAM does not need to be refreshed, whereas dynamic RAM does. That just means that every once in a while, since we're storing the information in capacitors, right, we have to periodically refresh the information or it's going to degrade over time. So dynamic RAM needs to be rewritten periodically, whereas static RAM doesn't. EDC in this column stands for error detecting code. That is something to do with making sure that we can detect, and eventually we also have something called ECC or error correcting code that allows us to fix problems that occur in cache memories. Now, here's a big important column, the cost. Notice that though static RAM is more stable, it doesn't need refresh, doesn't necessarily need EDC, it does cost about 100 times as much as dynamic RAM. And that's the reason that we don't just use static RAM for everything, right? I mean, if they cost the same, we could just load up a system with static RAM and everything would be fine. We'd be using the quickest option all the time. But that cost is a factor, and we don't want to spend a whole lot more on a system than we need to. So these different kinds of RAM end up getting used for different applications. Static RAM is what we're going to use for cache memories, which is the whole point of this module, and we'll be talking about moving forward. Whereas dynamic RAM gets used for main memories, frame buffers, etc. Now, dynamic RAM and static RAM are what we call volatile memories. They lose the information if we power them off. So if we just cut the power to them, all the information stored in there, all those bits just kind of go away. We can't get them back. We also have non-volatile memories that retain their value even if they're powered off. Read-only memory, or ROM, which is programmed during production. We have programmable ROM that can be programmed one time. Erasable programmable ROM that can be bulk erased with ultraviolet or X-rays. Electrically erasable PROMs have an electronic erase capability, so we can actually just put those into a device that can erase them without using radiation to reset everything. And we also have flash memory, and that we probably recognize, right? We have flash memory that have block level erase capability. And what that means is that we can erase part of it, but not the whole thing. And of course, this is how a USB flash drive is able to do what it does, right? We can erase certain things on it, but we don't have to just erase the whole thing like we do with some of these other things. But those wear out after maybe 100,000 erasing. So eventually your flash ROM is going to end up not being usable anymore. It's going to wear out just like anything else. So we end up using non-volatile memories for firmware programs. It's like BIOS and disk controllers and controllers for network cards, etc. Whenever you have to do a firmware update on something, this is what we're doing. We're actually erasing this non-volatile memory because we don't want the firmware for our disks and our network cards and our graphics cards to go away as soon as we turn the power off, right? We have to be able to turn off the system and have those things be persistent. We also have solid state disks, right? So again, thumb drives, smartphones, MP3 players, etc. And nowadays, laptops, desktops, things are moving to solid state because, as we're going to see in a little bit, it's a whole lot faster. And we also use this for disk caches. So since we're talking about non-volatile memories, let's take a look at a still very, very popular and common one, but it's getting less popular more and more. We're seeing more and more systems that have solid state drives instead of spinning hard disk drives, but it's still important to understand how they work. We still see these all over the place. So let's take a look at what's inside a disk drive. Now this graphic just gives you some labels for the various parts of the disk drive that kind of matter to us. So you might want to even pause the video here and just sort of take a look. It's pretty self-explanatory, but get an idea of what these terms mean and what we're talking about moving forward through the rest of this little section of the video. Now, to explain how all of those parts go together to actually store data and let us access it as quickly as possible, given the limitations of the fact that we're dealing with a physical drive that's spinning around, we have our disks, which consist of platters, right? Remember that from the previous graphic. And each platter has two surfaces. Now, each surface has concentric rings called tracks. If you've ever seen an old vinyl record player, right? These vinyl records, the same kind of idea, right? They've got tracks within these on these surfaces. Each track consists of sectors that are separated by gaps. So we've got our platters divided into the two surfaces that they have. The surfaces are divided into tracks, and the tracks are further subdivided into the sectors. So let's take a look at what goes into the time it takes to read information from a disk. Let's assume the disk just read data that's contained in the sector that's colored blue. The time it takes to read that sector is called the transfer time. Then it needs to read data from the sector colored red, so the next step is to find that sector on the physical media. Now this operation is called a seek. Then we have to have some time that's taken because the platters have to rotate to the right place for the actuator arm to actually read the data from that physical location. The time that takes is called the rotational latency. Finally, it reads the red sector, and then it does the same thing over again, right? It's going to transfer the data from the red sector, seek out whatever sector it needs to find next, rotate. We'll have that rotational latency while it finds the next sector it needs to read. Then we'll have the transfer when it reads the next sector, and so on and so forth, and it just keeps on doing that. Now, individual access times can vary based on where the sectors we're reading from are located relative to one another. So let's take a look at how we figure out the average times to access some target sector. And we'll have our access time is equal to the average seek time plus the average rotational latency plus the average transfer time. Now, what seek time, that T average seek, right, the average time to seek, is the time to position heads over the cylinder containing the target sector, right? That's the whole idea behind a physical disk is we've got to get that read-write head over the actual physical spot that the sector is on the disk. And the typical seek time, on average again, is somewhere between 3 and 9 milliseconds. The rotational latency is the time waiting for the first bit of the target sector to pass under the read-write head. Now, a pretty typical average rotation time is 7,200 rotations per minute. Now, you'll actually probably recognize that number if you've ever shopped for a hard drive, because that's one of the standard things that you look for. This RPMs is one of the standard things that go into the cost of a hard drive and to how fast it operates, right? And there are some a little more old-fashioned ones that are 5,400. You'll find some that are 10,000, right? 7,200 is a pretty good average, but there are definitely other possibilities out there as well, depending on how much money you want to spend. Finally, we have transfer time, which is the time to read the bits in the target sector. So this is where we're actually doing the reading. So we know that solid-state drives tend to be a whole lot faster than rotating disks. So why don't we just use those for everything? Well, there are trade-offs, right? As in with anything, there are some disadvantages of SSDs as well as a bunch of advantages. Now, advantages, there's no moving parts to an SSD, which means they're faster. They require less power to operate. They're more rugged, right? They've got less moving parts to break if you jar it around a little bit. However, they do have disadvantages. They have the potential to wear out. Now, there is this thing called wear leveling logic in the flash translation layer that does mitigate that. And for example, the Intel SSD 730 guarantees 128 petabytes of writes before they wear out, but still they're going to wear out eventually. And in 2015, at least, they were about 30 times more expensive per byte. Now, that's gone down as well, right? SSDs have become less expensive as time goes on, but they're still more expensive than the old school spinning hard drives. So we do have some trade-offs there. Some applications that they tend to be used for, MP3 players, smartphones, laptops, stuff where you have to have a decent amount of storage in a very small space. And then again, they're also seen much more often these days in desktops and even in servers, right? If we want very quick data transfer to and from disk, SSDs are a great way to go. Now, if we just want reliable storage that doesn't need to be terribly quick, it might make sense to save that money and look at old-fashioned spinning hard drives. So once again, as in we saw with static RAM, it's way faster and it doesn't require as much other stuff, but it's way more expensive than dynamic RAM. So it might make sense to use static RAM for some things, dynamic RAM for others. The same thing applies with solid-state drives versus rotating disks. Now, this graph shows 20 years of the various speeds of spinning hard disks, solid-state drives, dynamic RAM, static RAM, and CPUs. Now, as we'd expect, they're all getting faster over time, right? Access times keep getting lower, but notice that they get lower faster for CPUs. They get lower faster for CPUs than they do for static RAM, and that gets a little faster than it does for dynamic RAM, right? So we keep seeing the gap keeps widening, right? The old-fashioned hard disk drives get faster at a slower rate than CPUs do, and that means that this gap keeps widening. And the other thing just that we have to contend with is that the faster stuff costs more money. As we move through this list, a static RAM costs a lot more than dynamic RAM, right? Solid-state drives cost more than hard disk drives. The takeaway is that speed costs money. So we have to figure out how to contend with that. How do we leverage all these different technologies that operate at different speeds so that we can get as high a performance as possible while keeping the price points at a reasonable level? Well, in order to answer that question, we have to understand a concept called locality. So let's look at some definitions here. The principle of locality is that programs tend to use data and instructions with addresses near or equal to those they've used recently. All right, if I access a particular piece of data that's at a certain address, odds are very good that I'm going to access that address again, or I'm going to access addresses that are pretty close to it for my next data accesses. We have a couple different kinds of locality. And by the way, the same thing applies to instructions. Right? When I'm reading a program, when I load a program into memory, odds are that I'm going to be using a lot of instructions right nearby each other because, well, we've loaded the program into memory. It's probably in a fairly centralized location. So we're probably going to be accessing stuff that's close to each other in memory quite a lot. We have a couple different kinds of locality. We have temporal locality, which means that recently referenced items are likely to be referenced again in the near future. Right? That's our temporal locality. And spatial locality means that items with nearby addresses tend to be referenced close together in time. So we want to keep that in mind, the difference between the temporal locality and spatial locality. Now, that might seem a little abstract just to go from the definition, so let's take a look at an example. Here we have a very, very simple for loop that just loops through an array and sums up all the elements, then returns that sum. Now, we can see locality both for data and for instructions, and we see both spatial locality and temporal locality in this example. Now, remember that the elements of an array are stored sequentially in memory, so as we loop through, each element we reference is right next to the last element we referenced, right? If we're looping through an array, we know that it's all going to be packed together in memory. That's how an array has to be stored. So that's an example of good spatial locality because, again, as we go through, we're going to reference A at index 0, then index 1, then index 2, and we know that those are right next to each other in memory. Great spatial locality. We reference the variable sum with each iteration, right? So every time we loop through here, we're accessing that sum variable again because we got to read it, we got to increment it, we got to assign to it. So that's good temporal locality. Remember, the temporal locality means that if we access a particular item in memory, the odds are very good that we're going to reference either that exact item or something close to it very soon. Temporal locality in action. Same thing applies to the instructions. We reference these instructions in sequence, and there's our spatial locality, and we're cycling through this loop repeatedly, right? So that's our temporal locality. So this is a great example of both data and instruction references exhibiting both good spatial and good temporal locality. One thing to mention really quick, when we reference those array elements in succession, that's called a stride 1 reference pattern. And that's because we're just incrementing I by 1, which means we're looping through, we're accessing those array elements one by one. So every time we access one, the next thing we access is the one right next to it. Now, if we were incrementing this loop counter by 2, right, instead of I++, we've got, I equals I plus 2, then we'd be displaying a stride 2 reference pattern because we're accessing one thing and then we're skipping ahead by 2 to reference the next. Right, so the general form of this is called stride k, and that just means that it visits every kth element of a vector in memory. So again, a stride 1 reference pattern refers to a function that visits each element of a vector in memory sequentially, right? I'm just going from one to the next one. Stride k means I'm going to visit every kth element. So if I do that I equals I plus 2 instead of I equals I plus 1, I'm visiting every other element. That's stride 2. If I did I equals I plus 3, so I'm visiting every third element, well, then I'm got a stride 3 reference pattern. Now, being able to look at code and get just a qualitative sense of its locality is a key skill for a professional programmer, right? We want to be able to look at code and get an idea, hey, has this got good locality or has it got bad locality? All right, so the question here, does this function that we see here have good locality with respect to array A? Now, if we assume row major order, right? We assume and think back to the previous video where we talked about what row major is. That basically just means that every row is stored together, right? And we sort of string those rows one after another. Well, in this case, it does because that outer loop references the row. The inner loop references basically the elements within each row. So we're going to start out at row 0 and look at each element in row 0. Then we'll go to row 1 and look at each element there. if you think about how that's laid out in memory from our previous videos, then yes, we're just stepping right through address to address to address. We're not skipping around like crazy, right? We're not going to the 0 element for the first row and then jumping all the way to the 0 element of the next row and then jumping all the way to the 0 element of the row after that and then going all the way back, right? We'd have to do a lot of skipping around if we didn't do it this way. So this one, assuming row major order, does in fact have good locality with respect to array A. Now, if we had column major order, we wouldn't have that, would we? Right? At that point, if we had the columns stored together and then strung out in a big row, then we would have to jump around in memory, and so that would be bad locality. In this case, notice that all we've done is swapped around the for loops, right? We're referencing n first and then m. So this is the opposite, right? With row major order, we're got bad locality here, right? Because we're referencing columns first. So we're going to be jumping around in memory to reference each element that we reference in turn. With column major order, this would be how we would need to do good locality. So keep this example in mind. We want to think about locality as we write our code. Know what kind of system you're writing for, or what kind of as the systems by and large are going to be that your code is going to be running on. If there's a way to know, think about the way to order things. Think about how you put your code together so that you can display good locality in your code. So finally, we've got some fundamental and enduring properties of hardware and software that we've just talked about. We have fast storage technologies cost more per byte and have less capacity and require more power, and that translates to more heat, which has its own costs. The gap between CPU and main memory speed is widening, when well-written programs tend to exhibit good locality. We put all those together, right? These fundamental properties complement each other beautifully because when we put them all together, they suggest an approach for organizing memory and storage systems. And finally, this is what we're talking about when we talk about the memory hierarchy. So this pyramid shows us an example of a memory hierarchy. We've got it divided into levels, and notice that the smaller, faster, and more expensive stuff is up at the top, level 0, and the larger, slower, and less expensive stuff is down at level 6. Now, what these kind of sizes of these different levels as we go down this pyramid mean is that's how much data we're going to store at each level. So the CPU registers hold words retrieved from the L1 cache at level 1. The L1 cache holds stuff that's retrieved from the L2 cache, which in turn holds stuff received from the L3 cache. Now, those can all be static RAM, right? And, we've got more in the L3 cache than in the L2 cache. More is stored in the L2 cache than in the L1 cache, etc. Now, moving down past level 3, we get out to our main memory. That's our dynamic RAM. And that, like, when you're buying a laptop, like I said, when you look for a laptop and you say, oh, this has 4 gigabytes of RAM or 8 gigabytes of RAM, this is what we're talking about. This dynamic RAM that forms our main memory. Then we've got local secondary storage. That's our local disks, right? So, and it's a perfect example. I might have 8 gigabytes of memory, of RAM. That's going to be that more expensive and quicker dynamic RAM, whereas my secondary storage refers to the hard drive. I might have a 1 terabyte spinning hard drive in there or a 500 gigabyte solid state drive, right? That's our secondary storage, our local secondary storage. That stores a whole lot more information than the main memory is going to be able to. Why? Well, because even solid state drives are a whole lot cheaper per byte than dynamic RAM is, or we could just, keep everything in memory all the time. And eventually we've got at level 6 remote secondary storage. This is stuff that lives out there on the network, right? This is out on web servers, and that stores a whole lot more data because at that point you've got kind of anything that's out there available on the World Wide Web is, available to be remote secondary storage for you. Okay, one more term to understand, is cache, right? What is a cache? We usually think of these in terms of those L1, L2, L3, and that's another thing we'll see when we shop for computers, right? We'll find in the specifications for various, like a laptop that we might want to buy, the sizes of the L1, L2, possibly L3 cache. But what a cache means, generally speaking, it's just a smaller, faster storage device that acts as a staging area for a subset of the data in the larger, slower device. So really, in the memory hierarchy, every level is a cache for the level below it, right? L1 is a cache for L2. Main memory is a cache for local disk storage. So this is the fundamental idea of a memory hierarchy. For each K, the faster, smaller device at level K serves as a cache for the larger, slower device at level K plus 1. Again, that local storage at level 5, right, has a cache, but the cache for that is what's at level 4. It's the main memory. Main memory, its cache is going to be that level 3 cache memory. And so on up the chain. So why does this work? How does that make any sense, right? We're just adding more stuff to read and write to, aren't we? I mean, if I've got something stored on disk, why wouldn't I just go get what I want and dump it right into the CPU register? Why would I go through these other levels? Well, it's because of locality. Programs tend to access the data at level K more often than they access the data at level K plus 1. So the storage at K plus 1 can be slower, thus larger and cheaper per bit. But the memory hierarchy creates a large pool of storage that costs as much, roughly, as the cheap storage near the bottom, but serves data to the programs at the rate of the fast storage near the top. So when we think about why it makes sense to put those intermediate levels in, when I'm going to go do a read, I've got to do some stuff. I've got to go out. I don't want to just grab the specific word that I need and do all of these reads and writes like crazy. And because of locality, I know I'm going to need some stuff that's nearby, so it probably makes sense for me to grab kind of a big block of stuff. Not big, but some stuff around the word that I'm specifically looking for that's going to go into the register that the program is calling for in. So what I can do is go grab not just the specific address that I want, right? Not just the word there. I can grab a whole block, and I can keep that block in the cache above the register. I can keep that in L1, right? Now, when I go all the way back to disk for something, though, again, we have locality. I might span beyond that block. If I'm looping through a big old array, or if I'm executing a big program, maybe L1. Maybe L1's too expensive to store as much as I might like to, so I can actually grab a bigger chunk. I can grab a pretty big chunk from the local disk, store that, bring that into memory, main memory, take a somewhat smaller chunk around the specific address of the word that the CPU wants, put that into L3, a somewhat smaller chunk goes into L2, a somewhat smaller chunk goes into L1, then finally the word that I was specifically looking for gets to the CPU. Now, as locality takes its course and I'm accessing stuff that's pretty close, I could just, instead of going all the way back out to disk, I can just go to level 1 and use that really fast static RAM to grab stuff until I need something that we get outside of what that locality does for us, and I need something in a different area. But then, maybe I'm still dealing with some locality and I can just go up to level 2. And maybe if I've grabbed a big enough block into L2, if I'm just moving from one L1 block to, outside of that, but still within that L2 block, hey, I just grab that out of L2. Things keep being faster and faster and faster. So I'm delivering information to the CPU really fast because that locality helps me out. And this is why we want to code with good locality. We don't want our programs to run a lot slower than our competitors' programs because we haven't bothered to make sure we're using good locality. Good locality is what's going to make this memory hierarchy work, and it will make you see substantive speed increases to your code. So that does it for this first video in Module 3. What we wanted to get out of this one was just the idea of the memory hierarchy and the terms and concepts that go into why does the memory hierarchy work? Why is it a good idea? So the things to take away from this are that speed gap, right? Speed gap between the CPU, memory, mass storage. It keeps getting wider and wider. So we have to deal with that. And what goes along with that is, again, the larger, slower stuff is less expensive, right? So the slower the storage medium, the less expensive it is, which means the more I can afford to keep on it. As we get faster and faster and faster, it gets more and more and more expensive, and that means I can only afford so much, right? I can only afford to keep so much data in static RAM. I can afford to keep a whole lot more on a spinning hard disk. Also, locality. That is such a huge concept. Well-written programs exhibit this property called locality, and memory hierarchies are based on the whole idea of caching. We close that gap by exploiting locality.